and we are live. So this one should be going live pretty well. So we've now talked about the derivatives. We skipped the implicit differentiation, and we got to what is called in chapter 4.10 antiderivatives. And we haven't talked about the integral yet, but we started to talk about this. So obviously, when we have the derivative as an operator, so we take a function, we apply the derivative to it, and then we get another function. I mean, if we think about the derivative as a function, really it's, we explained that the value of the derivative gives the slope of the tangent line, but you can just as well think of it as a transformation that we apply to the function, and after the transformation, we have what is called the derivative. Again, just through various examples that you can look, you can think of it as it gives you the rate of growth, the instantaneous rate of growth of that function, or that it gives the tangent line of the graph of the function in the point, the slope of the tangent line, or you can just think of it as a way of approximating it linearly, like in what we explained in the slides that I made, and so forth. But this begs the question, if we think of this as a operation on the function, what is its opposite operation? And I don't like to think of it this way. One reason being that it's not injective as an operation. I mean, if you think about all the possible set of all functions, and of course, not all of them are differentiable, but let's just consider all differentiable functions. Then take the function, constant function whose value is 1, and take the other constant function whose value is 2. So both of these have the derivative, which is 0 at all points. So it's not injective. You take two different functions and their derivatives are the same. So if you think of the derivative as a mapping from functions to functions, that mapping is not injective. However, it is actually only this constant function that I mentioned that has this property that its derivative is 0. Well, technically this is not entirely true, but of all the continuously differentiable functions and all the functions barring some really pathological functions, we can say this is so. So sometimes called the antiderivative is the operation, it's the function whose derivative is f. And in general, for each constant, I mean, if you vary it with a constant, take x squared, or here are some examples. If we have x equals 3 to the x squared, finding it as antiderivatives, well, we can try x to the 3, and x to the 3, you differentiate it, you get 3 times x squared. So definitely it is an antiderivative. No, not the or the antiderivative, an antiderivative, one of them. But also 3x squared is the derivative of also x to the 3 plus 5, x to the 3 plus 1.012, and so forth. So anything added to it, any constant. So every function of the form x to the 3 plus some constant c, it has a derivative x, 3 times x, sorry, should have had more coffee, 3 times x to the 2. And think about 1 over x. Well, we already saw that the logarithm of x, we take the logarithm of x for positive numbers, that results in 1 over x as its derivative. And if x is negative and we take the logarithm of minus x, then that's actually minus of 1 over minus x, and that's 1 over x. So in fact, if we have the logarithm of the absolute value of x, then its derivative is 1 over x for, well, for all x. And add any constant to that, that is also what is called the antiderivative. So this is a valuable thing to do, and we need to find this. We will shortly see something which is called the fundamental theorem of calculus, which don't have to bother yet, but it ties down what is known as the integral and the antiderivative, if you will. I'm not a big fan of the idea of indeterminate integrals or antiderivatives, simply for the sake that, it's ambiguous in some sense with this plus c, some constant. Let's go here. So the sinus of x and cosinus of x, e to the x and so forth, that's fine. So sometimes we call this the indefinite integral. So the indefinite integral is easy to define in this way. And that's why I dislike it. It's easy to define, but it's mathematically, its meaningfulness is questionable. But it is commonly used and it is helpful. It is helpful as a tool, right? So the indefinite integral of f of x is found by taking an antiderivative of f and then adding any constant to it. So we use this indefinite integral sign, but this seems ridiculous or weird. Why is this f of x between this dx and this sign? And it'll be explained shortly whence this comes from. Here are some examples, like if you have 2x and you find its antiderivative, then it's x squared plus c, and the c can be any real number. So we don't know which of these we are talking about, and the indefinite integral means exactly that. It's not definite, it's not set anywhere. We don't know which one of these functions we are talking about. So it's not defined. And all the rules that we have for differentiation, we can use them backwards. But this requires a little bit of thinking how we find them and so forth. Power rule, we can turn it backwards, right? Because if you differentiate or find the derivative of x to the n plus 1 over n minus 1, then its derivative is x to the n over n plus 1 times n plus 1, so that becomes x to the n, as long as n is not equal to minus 1. Similarly, we can find all the differential formulas and all the indefinite integrals. Here's a nice thing. I wouldn't recommend you learn this, especially not for these somewhat more complicated formulas. But we decided we don't talk about that much about these derivatives of these derived, contrived, trigonometric functions like the secant and the cosecant and so forth. So there's no point in us talking about that. But here are some of the inverse rules. We didn't actually prove this. This is a fascinating thing. The inverse of the sinus function, we can find its derivative. We didn't talk about that. I'll put it in this week's exercises. We are going to need to calculate these at some certain times. The inverse tangent and so forth. So these things will come in handy, but we haven't proven these yet. These will come in next week's exercises, these differentiable rules. We're actually more interested in the basis in which we use the simple cases, and then later we will have more differentiable rules about the inverses of the trigonometric functions. We didn't have the time and scope to discuss them, but you can you are fully at your liberty to refer to page 489 in the book whenever you have to think about what is the derivative of certain function or what is the integral of certain functions. Then you can find them in here. So here are some examples. you should verify the statements. Not going to go in there, not too keen on doing this. All the similar rule, most of the same rules as derivatives, they apply here. So taking the antiderivative or taking the integral is linear in the same way as taking the derivative. Multiply it by a constant, that is, you know, take the integral of or the antiderivative of something that is multiplied by constant, then it's simply that constant can be first, you know, you can put it aside, find the antiderivative, and then multiply with that constant again. And I'm going to have some, you know, some questions, you know, find these integrals and so forth. There are lots of tricks and things to do. And sadly, we cannot omit all of them here, but I'll show them, but I'm not expecting you to become, you know, this is, I mean, I'm just going to say it out, like, this is the toil and turmoil of learning to do these more complicated, even rational functions like these, taking these similar to this, it very quickly becomes, you know, toil and turmoil of biblical proportions, like, you know, fire and brimstone, meaning, you know, you can spend hours upon hours trying to figure out something if you do it by hand and still not get the answer. These can get really, really hairy and difficult. That's what I'm saying. And my purpose here is not to expect you guys to become experts at applying a big cornucopia of tricks with which to find the integrals or the antiderivatives of pathological functions like this. But even though that's not my goal, there will be some things, some tricks that we will have to learn, and I expect you guys to actually do and manage. But my focus will be on trying to understand what the integration means and what it's supposed to do. So there are solutions here, and I will refer to you to do these things and so forth. But we will encounter later what we call a differential equation. And, you know, differential equations are the salt of the earth, if you will, of continuous mathematics and analysis. I mean, when you are modeling something, just about anything, be that planetary motions, be that electrical circuits, you know, current and voltage in electrical circuits, or you know, just about anything, you will encounter differential equations. That means that a differential equation is an equation where the derivative of something depends on the value of that something, and maybe the second order derivative of something or the third order derivative of something depends on the value of that something, and then it's expressed by some function. So a simplest kind of differential equation here will be known like this. So the derivative of y with respect to x is some f of x, where f of x is known. So basically, if we know that the derivative of y with respect to x is 6x squared, then we can find y by simply finding the antiderivative, meaning taking the integral of this, and whenever y is something like 2x to the 3 plus c, then it will satisfy this equation. But more often than not, simple equations like this are not going to explain how your system behaves. Like, take an electrical circuit, for instance. If there is let's say there is a capacitor there, then the voltage in the capacitor, you know, depends on the current, you know, well, in fact, it depends, Well, okay. I was going to talk crap. So what I'm going to say here is that it's pretty complicated. So that results necessarily in second order equation. I'm not going to go there. I'm not going to go there now. I'll use that as I have that as an example, but it results in second order equation. I'm not ready to do that yet. Okay, so I don't know how have a very good example at this point for this very simple case. But the derivative of something, the speed, the speed of the train depends on how far it is how far it is from the station, right? Your x is the distance from your station, and the derivative of x, which is the speed at which it's going away, is depends on that, how far it is. But we don't know what the solution, because if we just apply the antiderivative, we get one of them. We don't know which one it is. There's always that constant. However, if we have an initial value x0, and we know that the value is y0 at that. For instance, we know that the train stopped at that station, and its speed has increased by, as it's gotten further from the station. We know that then we can calculate this, because when x is 0, this 2x to the 3 plus c must be 0, so we get that this c must be 0. If this initial condition is something like y at 1 equals 5, then we just have this equation, we slip in 1 here, so that's 2 plus c equals 5, and we conclude that c equals 3, and we conclude that the solution to the initial value problem is y equals 2x to the 3 plus 3. So this is often the way we will solve later these differential equations. They will come, we're not going to learn it yet. I'm not going to ask you to solve these differential equations yet. We'll have some at the end of this course, just some very relatively simple examples, because really that's, if you use the differential and integral calculus, if you use the derivatives to model something, then you will get differential equations, and that's really why they are there. It's really, it's very often, I don't know of any practical implementation or any practical engineering problem in which you use the derivative that does not result in a differential equation. So the differential equations are the thing that we are aiming for, really. Here are some examples of initial value problems, how you solve them. But, that's just one way to look at the integral or the antiderivative. We find the indefinite integral, then solve what that c is by looking at what its value is supposed to be at certain point. So you get the constant from that point. Here are some examples. I'm not going to go here. Here's an example of a decelerating car. These so-called practical examples, they're often very contrived, because that's not really very, it's very rare to encounter these in real life situations. So here are some exercises that you might want to do. I'll put some of these in next week's exercises, and we'll also learn some of those derivative and antiderivative rules for next week. But then I'd much rather, I really do urge you guys to read whenever we're done in some situation, whenever we're done with a chapter, or we've covered some chapter, I really do wish that you would read all these key terms. See that chapter 4 doesn't have many key terms that we've covered, because that's we only covered this antiderivative part, so we don't have to worry about that. Number 4 chapter is not that much, and of course the L'Hopital's rule, that was important as well. So I'm just going to skip these. We're going to go to exercises soon enough next week. And now we will talk about what is called integration. And very often, more often than not, we it is taught, integration is taught this way, that use summation of approximating areas. You know, you have some sum over some region. Here's a lot of this and that about sums and so forth. We will talk about these sums and sigma notation a little bit, but first, and we'll get to that. So I hope you're familiar with sigma notation. When you are adding stuff together, you have an index I ranging from 1 to n, and then you add something that depends on I. Well, this doesn't depend on I, but here's just, oh, sorry, this wasn't defined very well here. So this is the definition here. So in the sigma notation, this means that we sum over some index I to the 20. So this means there are 20 terms to be added. Usually the term to be added here depends on I somehow. It can be indexed like a index I, meaning that you may have some set of objects like the first, the second, and so forth, the 20th or nth, and you add them. This means you add them together. Those of you who are familiar with programming, like you have a for loop or something, and you can think of this as a for loop, but don't think about that too much because we will talk about indefinite sums as well, in which the n goes to infinity and so forth. Shortly, later. Not going to spend an inordinate amount of time. I'm expecting this notation to be familiar to some of you. If it's not, then read up on this and how the sums work. Obviously, if you sum these because of the way that the sum is commutative and associative, then if you are adding terms where there's AI plus BI, then you can just add the AIs first and then add the BIs and then add those together. And if there's a difference between AI and BI, you can add the AI first and then subtract the BI and so forth. The product is not necessarily, you can also cut the sum in two, like there is a sum from I to M, and then there's a sum from M plus 1 to N. And this is fairly simple stuff, and I expect you guys to be aware of some of these. There are some simplistic rules that you can learn. I hope that these are familiar from this. We'll revisit these a little bit later, a little bit more. You should, the only thing you really need to be is to be aware about this, understand this notation, what it means. I'm not going to go here. So here's the problem. So let's say that we have a curve, f of x, and then we draw that curve from A to B, and we want to know the area, we want to know the surface area that falls under the curve like this. So most of you have already learned that we can use the integral to find this, but let's have this topic, or this approach, is what we call the Riemann integral. We start by approximating it. So the simplest approximation of this would be simply to just take the value at A and draw a rectangle right here. Let me see if I have So we could draw this rectangle here, right? And calculate that area. Let's call that A plus. Then we could take the lowest value here. It's right over here, the minimum value there. And we take that and we call that A minus. So it's obvious that the actual area is something between A plus and A minus, right? That's obviously we have an upper and a lower limit for this, right? So if we use A plus, then we incur, we take this much. I'm trying just this area here and this area here are neglected if we take the A minus, and if we take the A plus, then this is added needlessly. So these are not correct approximations, obviously. Well, one way to make it more accurate is to divide it into smaller, divide it into smaller pieces. So here we propose we take the whole B minus A, that's the length of this area, divided into n pieces. I'm going to draw something like this. You know, like in my case, I'm doing a few pieces here. Sorry about that. So these blocks, they're not equally big, but you get my meaning. So I can take, let's say I take here the middle point and I take this, take here the middle point and I take this. I can also take the high point and the low point. So I know that it's somewhere in between here. Here I take the middle point that's there and the high point and then the low point somewhere between here. This one, the high point is here. The low point is here and the middle point is somewhere in here. See, I'm trying to, this is the low and middle. So these are just approximations here that, it's this block, the width times this height is the upper limit. The lower limit is this width times this lower height. And a better approximation might be somewhere in between. So there's somewhere in between, which is a correct height for this to get the area. So that the left out and the superfluously included areas are roughly equal. So as we make these smaller, these boxes, then you see that this error here, tends to become smaller. That's our idea. So I'm going to clear this again. So here's an algebraic intuition about it. So we begin by dividing the interval into sub-intervals, and we select points here. This would be x0 is A, xn is B, and then the next one is 1/n of the way forwards. And let's just call this delta x, this 1/n. How much distance is there from the one point to the next? And I'll just annotate a little bit more. So if this is my next stop, then this distance here, that's my delta x, right? So I have some number of those here. So this is the point x1. So each vertical line resides at the coordinate x0 plus I times delta x, where I ranges from 1 to n. Now, we call this division of points a partition of this interval A, B. So it's the partition. So we partition it. We look at these smaller boxes. We have a big box, that's A to B, and then we divide it into smaller boxes. We call this a partition. So from x0 to x1, then x1 to x2, and so forth. So these are the midpoints, x1 to xn minus 1. Those are the midpoints, and the endpoints are x0 and xn. So we can construct two kinds of approximations. So one, we can construct a rectangle with the width delta x and the height equal to the function value at the beginning of that interval. So here we see that construction here. So here we just assume that it continues as a constant, the function, not the slope, the constant. It continues as a constant and then stops. And then it jumps here, constant, stop, jumps here. It could go up or could go down. So these are maybe upper or lower estimates don't know which one it is. So the area, depending on how the curve moves, is approximately, but not quite, equal to the function's value at x0 times delta x plus the function's value at x1 times delta x plus and so forth, plus the function's value at xn delta x, right? So we get an approximation of the area. It's called the left point approximation because we assume the function retains the value at the leftmost endpoint, right? So this is the area. It could be slightly bigger, could be slightly smaller than this. Then we can construct the right point approximation, in which case this is called Ln, and n here is a parameter that depends on how many steps did we take. Remember that we assume that this n, we are constant intervals using here. We can use those same constant intervals for the right point approximation, meaning we take this, instead of using this point, we could take this point and then have that as the height of the first one and so forth. So we add xi, remember here it was xi minus 1. So at the beginning of the interval is the multiplier is taken as the height times delta x. Here we take the end of the function's value at the end of the interval times the delta of x. So we get two approximations. And the thing is, both can be too big, both can be too small, or one can be too big and one can be too small. We don't know. We don't know. But as long as, let's say, the derivative of f, if the slope of f doesn't wiggle around, right? Then if one is too big, then the other is too small. Okay. So here is some example of it. We can have the graph of x squared over 2 from 0 to some point. So sorry, it's here from 0 to 3. And here's the left point approximation, and here's the right point approximation. We get some values for those. The left point approximation gives us roughly 3.4375, and then the right point approximation gives us 5.68745. So they are different, and it's clear from this picture that this is going to be bigger than this. So we know that the area under the curve from 0 to 1 is, because this is now increasing, because this is constantly increasing in this, then the right hand side is going to be an over approximation, and because it's increasing, then the left approximation is going to be an under approximation. This is going to be lower than the actual area, and this is going to be higher than the actual area. The reason is that it's increasing, this function. So assuming that the function is either increasing or decreasing in this interval, one of these is an upper approximation and the other is lower approximation. If it starts decreasing again at some point, then around that point where it changes from increasing to decreasing, we have no idea which is better, or if both are, which is upper and which is lower, because even both can be. You draw a picture of that, but if there's if we take this original example here, then in here it changes from decreasing to increasing. So while we approximate the area before this point here, then the left approximation will be too big because we will draw the rectangle thusly, and the right approximation will be too small because we draw it like this. But after this point, the left approximation will be too small and the right approximation will be too big. And if we're very close to this point, we don't know which one is bigger, if either is bigger or both could be too small or both can be too big. Okay, so now we have two ways of approximating it, but what can we say about that? I'm not going to have this approximation. If we increase the number of rectangles, then the sum becomes, we would expect the error to become smaller. And indeed it does. The left approximation for increasing function tends to go up, and the right approximation tends to go down. Here are some examples, not going to go over these. And this area we can use, I mean, as long as it's either increasing or decreasing inside the box. And now we can make the boxes so small that the point at which it changes from increasing to decreasing will always be just in one, you know, at the edge of two regions. So we can assume that one is bigger and one is too big and one is too small. But it turns out that because, you know, one is, you know, I'm just going to write it like this. One is fxi times delta x, and the other is 1 fx minus I minus 1 times delta x, right? So we have these two, for each box, we have these two approximations of each, for each box. One of these two is too big and one of these two is too small, right? But remember the intermediate value theorem, right? So this is a continuous function. So between xi and xi minus 1, if one is too big, there is some number that is correct. Let's call that z times delta x. Let's say that the actual area inside the box is z times delta x. So we know that z is between xi and xi minus 1. Z, you know, sorry, fxi and fxi minus 1, right? Z is between these. And the intermediate value theorem then guarantees that we can find an xi star such that f at xi star is z. Now, using the intermediate value theorem, we guarantee that we can find an xi star such that that the function's value at xi star is z, and this xi star xi star will in fact be between xi minus 1 and xi. The intermediate value theorem guarantees that. So if we were to know this x star, and let's say that if we knew it correctly, then this area would be exactly correct. But regardless of which point we use here, we get some kind of approximation, and then unless the function is, you know, absolutely horrible at that point, then this will be a pretty good approximation as long as n is relatively big. So this sum, we call it the Riemann sum. So the Riemann sum gives us an approximation of this, area. And now what we intend to do here is, given that this delta x depends on n, so it's the smaller than n, then finding the area, and this, remember this xi star is some number in between or somewhere in that region. And we know that somewhere inside that region, this xi and xi minus 1 and xi, there is a point. X star, I star may not be that point, but there is a point at which this box is exactly this big. There is one point. We don't know which it is. It's probably not the endpoints, but somewhere in between it is. But the smaller, as we let the limit, as we let this interval grow to 0, then at the limit, it doesn't matter what point we take, there will, when we take an infinitely many of these, when we approach infinity, then in how many points we take or how many rectangles we take, this xi minus 1 and xi go towards one each other. So the difference goes to 0. In other words, this delta x goes to 0. So this is called the Riemann sum, and the A, the area, is exactly the limit as n goes to infinity, the sum of I goes from 1 to n fxi star delta x. And it doesn't matter which xi star we use in the interval, because at the limit, well, they will be the same. Well, not the same, but you know, that they'll be so close to one another that it doesn't matter what it is. This is, I don't like the Riemann sum. I do like the Lebesgue integral definition a little bit better, but I think this gives a nice idea of what is going on here. So we are kind of, this can be thought of as we're kind of approximating the area with smaller and smaller pieces. And as the size of the piece approaches 0, then this sum over, well, the number of terms in this sum goes towards infinity, but this product fxi delta x, that goes to 0. But there are more and more of them, and this converges towards this A. So this is another very good explanation of the Riemann sum. There are graphical demonstrations that I urge you to look at, and I'm not going to go there now. We're going to talk about these examples I'm going to put some exercises in which we talk about these examples. I'm really sorry that we have to kind of gallop through this stuff, but really, I urge you to look into this idea and understand that we can use any point in between, because the intermediate value theorem guarantees that there is some point in between in which the approximation is absolutely correct. And then as the gap narrows, then as long as this is some number, some point between those two, it must approach the actual value at which it is correct. Because there's not any room to move. But this assumes that the function that we are finding the integral of is in fact continuous. If it's not continuous, then this approach doesn't work, because the intermediate value theorem doesn't work. So this sum characterization only works for continuous functions. So I'm going to skip this finding the upper and lower sums and so forth. Here are some exercises that I will pick some of them. And then we can call this what we know as the definite integral. So really, this Riemann sum, when we take it at the limit, we can define this. And now this is called the Riemann integral. This is not the integral, it's the Riemann integral. And we talk about the Riemann integral, but if you study analysis further, you will encounter functions such as the Lebesgue integral. And those are more general in nature because they don't require the function to be continuous. This approach, for it to be correct, I didn't make the proof that this converges or something, but I justified my approach, or justified the approach by saying, look, this xi star that is picked from that interval, it can be anything because it converges to the value that exists by invoking the intermediate value theorem. But the intermediate value theorem can only be invoked if we're dealing with a continuous function. So we can only say that this Riemann integral can be calculated if we are dealing with a function that is continuous. I need to make this explicit. It may seem to you that I'm talking here, and I am. I'm just talking. But I tried to make it explicit that we can approximate the area, and somewhere in between there is a correct value which we can use in the approximation. And that's why we can say that this converges towards the actual area. But like I said, the integral as a Riemann integral makes sense only when we're dealing with continuous functions. And that's really, really, really important to understand. So if we deal with functions that are not continuous, then we have to do it piecewise. So we have to find the area from one discontinuity point to another. And then if there's a sudden jump somewhere, then we have to find the area from that. We cannot use the Riemann sum over that gap. So for example, if I have a function that behaves like, let's say I have a function that behaves like this. There's a sudden jump. Then if I draw a box here, right? And then the area is actually that darkened area. And these intermediate values from this point to this point don't exist, right? So we can't say that there is a value in between that corresponds to the height of the correct approximation height of that box. So if this limit exists, the fx is said to be integrable or integrable on the value on the interval AB. It's an integrable function. So this f of x dx, this dx comes from this delta x here, and this delta x here is approaching 0. So this is, you can think of it as we are adding all the points between A and B times, times the, all the teeny tiny infinitesimally small boxes, not points, but boxes, 0, all but 0 width boxes, and the width being this dx times f of x. That's our limit. Well, continuous functions are integrable, and if f of x is continuous, then f of x is integrable. And my argument that I made was simply it was made simply because, hinging on my argument hinges on the idea that it is in fact continuous, and I used the justification of the intermediate value theorem there on that. And in fact, I don't know if can be used. The nature of discontinuities, that depends on there. If it has a finite jumps or discontinuities, we can still integrable. We can find them integrable as long as we make sure that if there is a jump, then the edge of the box is at that jump, right? It's always at that jump point, so that we are calculating the area to the left-hand side of the box and then to the right-hand side of the box where the jump is exactly at the midpoint between them. So then everything works. If there's a finite number of discontinuities, everything works fine. But what about a function that is 1 at every irrational point and 0 at every rational point? Is that integrable? Not in this way. I mean, we cannot box in the area because at the lower limit it's 0 and upper limit is 1. However, we could use there is a technique which we can find the integral of that, but it's out of scope for this course. Just be aware that this is not the end all be all of integrations, this Riemann integral. It's not all there is, but it will do as long as we're dealing with functions that are constructed from elementary functions that are not elementary. If we construct piecewise constructions with finite number of pieces of the elementary functions, then all of those will be integrable and there's no problem. Of course, piecewise and of course excluding discontinuities. And then we have problems with situations where they go towards infinity. We have to see if we can integrate those. So how do we evaluate this integral using this definition? Let's have a 3-minute break. now. And I'm going to put some now. But it seems like the picture is, oh, now it's working again. Okay, good. Okay, so let's look at this example. We first want to set up the Riemann sum. So the delta x will be always of the form something over n, because that's the width of our window, and it depends on n, and the width of the whole integration area, in this case it's 2, and if we divide it into n pieces, that's 2 over n. So each xi, the point, the midpoint, will be that beginning point x0 plus the ith midpoint, I times delta x. Because delta x is 2 over n, then this will be I times 2n. So it's 2 times I over n. That's each of the midpoints. So we can calculate the right endpoint of that interval at f equals xi. And remember, we argued that it doesn't actually matter which point we use from the interval, because this number of this interval goes to infinity, and the endpoints, the difference between the endpoints goes to 0, so it doesn't really matter which we are using. So it's easiest to calculate usually with the right-hand side endpoint. In this case, we start with 0, and xi is at 2i over n. Then f at xi will be xi to the 2, so that'll be 4i squared over n squared. And if we take the Riemann sum, then we find that fxi, that's 4i squared over n squared, times 2 over n. And we see here that that's 8 times I squared over n to the 3. And then this 8 times 8 over n to the 3, we can take this as in the front here. And we only have the sum as I ranges from 1 to n. So we didn't cover yet how to calculate these sums. We will look into that more closely next week, but I'll put some exercises for next week on that. But we will look at that more closely. Here the idea is best, so we can look at it from the table, or look at it from ask Wolfram alpha or something. What is the sum as I ranges from 1 to n over I squared? And there is this term where there's a 2n to the 3 plus 3n 2 plus n, and that divided by 6. So when we make this into a more neat form, then this Riemann sum at the given n will be 8 over 3 plus 4 over n plus 8 over 6n squared. So now as n goes towards infinity, then the bigger the n is, then 4 over n goes to 0, and 8 over 6n squared goes towards 0 as well, because we're dividing with n, and as n gets bigger and bigger, then this term goes to 0. So this Riemann sum, this Riemann integral all from 0 to 2 is 8 over 3. So that's fine. So I'm going to now give you a group assignment, use 10 minutes or so. Find this 5.7. Use the definition of the definite integrals to find this 2x minus 1 integral from 0 to 8. And focus on formulating this sum. What are the terms that are going to be summed? If you don't know how to evaluate that sum or find the limit, don't worry about that at all. Just focus on basically getting to this point here. Focus on getting this to this point. What is the sum? What are the summands? What do we need to add, and so forth, right? And we'll discuss that. I'll divide you into groups now. There will be 4 people in the group. Just say hello to each other first. Discuss your weekend plans for about 1 minute. And then whoever has the wildest plans will be the person in charge of reporting your terms, your sum. You know, what is the sum? I mean, just the sum as I ranges from 1 to n. So you can write it like this: sum I equals 0 to n, and then sorry, 1 to n. And then, you know, in this case, it would be 4i squared over n. What is the thing that is to be added? So discuss it, and we'll get back to this at 3:15. Really, really sorry that if the time for the group session wasn't long enough. We are running out of time a little bit, so I have to get this show going. So what is groups? Group 1, did you get this sorted out? So did group 1, group 2? Okay, you didn't. What about group 2? No. Group 3? Was it that there wasn't enough time, or did you not figure it out? So let's do this. Let's do this. Let's do this. Let's do this now. So yeah, no. Okay. All right. So was it too short a time? Okay. 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 It was too short. All right. All right. All right. So I'm going to do it here. So we're looking for the sum as I ranges from 1 to n of, then we need some fx star, xi star times delta x. And we need to figure out what that delta x is. Okay, well, the delta x is pretty simple. So we're dealing with delta x. So we're dealing with the interval a is 0, b equals 3. So delta x is equal to, well, basically it's 3 over n, isn't it? So if we divide the length of that, the width of that region is 3, and if we divide it into n equally sized pieces, that's 3 over n, right? And we need to figure out what xi is. Well, xi is obviously x0 plus I times delta x, which is 3 times I over n, right? So our sum of fxi, okay, as of, and the sum is of what? Well, it's of f at x times delta x, so that would be 3 times I over, it would be 2 times 3 times I o over n minus 1 times delta x, right? That's what the sum, you know, the sum as I ranges from 1 to n, which is equal to the sum of, and I'm going to just then write that down. So that comes the sum as n, sorry, I equal 0, 1 to n of, and now we multiplied it by delta x. Well, the delta x is 3 over n. So that would be 2 times 3, that's 6i times 3, that's 18i over n minus 3 over n. Right. So this is pretty much what I was just expecting here. I wasn't expecting any more than this. This is what I was expecting. This, now we have the sum. So we can figure out what that sum is. So, well, that's we can take the 1 over n and the as a coefficient, and there are two sums as a subtraction. So I'm just going to write sum of so that's 1 over n times 1 over n. Take the first term, that's 18i over n. So I'll take the 1 over n times the sum of 18i, then minus, well, that's just 3, isn't it? Sum from 1 to n, 3 over n. We add n of those together, then that's just 3. And the sum of 18i, well, you can figure it out yourself later. Then when we have this is, oh, sorry, there was one missing. That was 18 n over n squared. Sorry, I'm sorry. That should have been n squared, right? So that should be 1 over n squared. That's what we should have. And then we could just calculate that sum. I'm not going to go there because that's not yet something that we learned, but formulating this sum is somewhat important. It's the important part. All right. So that's one way to do it, is to figure out this sum, but that's actually going to be really, really tedious. Why would we do this for several functions? This will be terribly inefficient and really hard to do. So we won't be able to do that in general. Here's some example of finding regions when you know the area and so forth. I'm not going to go here. So we look at this integral and the area thing here. This integration here gives the net area, really. I mean, it gives the net area so that you get the negative and the positive. So that needs to be taken into account, that there is the negative area and then there is the positive area. So the integral from here to here is not the sum of these, but the difference of these areas, obviously, because this is on the negative side and this is on the positive side. So, not going to go here, not going to do this all that much. There's a lot of ground to cover there, but you know, I think that one of the dangers of the area thing is that you may overlook this. It's possibly easy to find the definite integral. So here are some rules. So any integration from a point to itself over just one single point, that's zero. There is no area under one point. If you reverse the order of integration, you get the negative of that. And that's simply because you know this is very dangerous from the point of view of intuition that we just said. It shouldn't depend on which direction we go, but really when we are dealing with this, if we are calculating it backwards, then we should be really subtracting the area if we're going from right to left. That's the most contentious of these 5.10. So I would really, the intuition of why this is so is something that you just have to take it into account. So that if you're going backwards, you're subtracting. If you're going forwards, you're adding the area. You can add fx and gx, and this is linear. This is basically means that it's linear. If you're integrating over a sum, you can integrate them separately. Difference, the same thing, integrate them separately, and multiple. So these three, basically 3, 4, and 4 follows from 5, 3 and 5. So if you take 3 and 5, then it means that integration as an operation is linear. Any linear combination of functions is simply the integral of that is the linear combination of the integrals of those functions. You can split it into split from A to B, from A to C, and C to B. And for this to be true, we need this to be true even when the C goes outside the A and B. I mean, this works even if C is bigger than B. If A is smaller than B and C and B is bigger than, C is bigger than B, then this definition works if we assume that reversing those results in negative. That's why it needs to be so. So here are some of the examples of the properties you can use this linearity and this to have. There are this called comparison theorems. If you integrate over a positive function, then its integral will be positive if you integrate from left to right. That should be obvious. If f is larger than or equal to g and you integrate f over a region, then its integral over the same region of g is the same. The integral of f over a region is larger than or equal to the integral of g over the region if f is larger than or equal to g in that region. And the thing is, if small m and capital M are constants, such that m is smaller than f of x at all values between a and b, and capital M is larger than or equal to f of x in all of a values between a and b, then m times b minus a is smaller than or equal to capital M, or than the integral, which is smaller than the capital M. This is simply that if you take the box of the largest value of f and the smallest value of f, if you take the upper limit and the lower limit, that one box, then the integral resides between those. That's simply stated it. Now, here are some comparisons. You can compare functions over a given interval and compare their integrals, if you will, if you want to. Not going to go into this definition all that much. You can calculate the average value of the function here. Really, here, you can generalize the concept of average. The average function, you know, or I don't really like this idea of average value of the function because the value is really, but we can define the average value of a function on an interval can be thought of as the integral of the integral over that region divided by the width of that region. So, you know, in fact, what happens is that the average, if you call the average times the width is in fact the area. So if you think of it this way, you know, if you had a box whose width is this, then its height should be the average of the function's value in between for its for the area of that box to be equal to the area under this curve. That's how you can define averages being that height. Okay. I think we will stop here. This is the part of the integrals. I would really like you guys to look at these examples. I'll put some exercises on Monday online so that you will be able to rehearse them, and we'll talk about them during the exercises as well. Next week, what we will do is we will move towards this fundamental theorem of calculus. The fundamental theorem of calculus is really powerful. I'm going to state it now before we stop for today. And the fundamental theorem of calculus states that if you have the integral, definite integral from a to some point x of ft dt, so you're integrating, f is a function and we're using its value t here. We're integrating from a to x. Now x is the, this f of x tells you what the integral is if we start from a and get to the point x. So the function, this is a function of how wide we go here. Then the derivative of this function is exactly f at x. This is the fundamental theorem of calculus. And this ties together the antiderivative. That's why we call the indefinite integral the antiderivative of that. That's, I think, instead of ever talking about the antiderivative and having this concept of having the value c there, the constant, and so forth, I would much rather us to just have the definite integral and then use the fundamental theorem of calculus, because there's no need for us to talk about this indefinite integral. It's a handy tool when you calculate it. And here's a proof of that, and we can prove it fairly simply using this. It comes down to the derivative with respect to x and so forth. But we'll talk about that next week. But really, I mean, I think the important idea of the integral is probably the Riemann sum gives the important idea of the function, because really we are adding stuff together. We're massing up the stuff under the curve, if you will. We're amassing. You can think of the function as giving some kind of density or propensity or flow or flux or whatever, and then the integral is the cumulated stuff that you get. So I was going to mention earlier the circuit. So you have a capacitor. There's a current that goes in the capacitor. So the charge inside the capacitor grows with the more current there is. Of course, it has a limit as to how much it can carry. The voltage increases as well. But the integral over the current is in fact the charge inside the capacitor. And then when the voltages cancel out, then the current goes to zero, but that's not the point here. The point here is that it ties together both the derivative and the integral in a very nice way. And that's why I think it's a bit of a shame to think of the integral as the reverse of differentiation. Instead, the integration is one thing and the differentiation is another thing. And then the fundamental theorem of calculus tells us how they tie together. They tie together so that, the margin, the marginal increase in your, whatever the quantity is that you are amassing by collecting stuff that this f of t produces, then the marginal increase of that is this f. So that's why the derivative of this f, capital F, is the small f. All right. I'm sorry that the group session, in the group session, you didn't have enough time to do the whole thing. I hope you got some idea about what needs to be done, formulate the sum. I hope you have the idea to formulate these Riemann sums. I'm not going to ask you at this stage to actually calculate the Riemann sums and find what their limits are. I'm just going to ask you to formulate them. And that's the important part here. And I'm going to put some exercises for next week on that. Are there now any questions before we stop for today? I'm going to stop the recording.